and good morning, colleagues. If there are any teachers who are watching this program today, I'm going to be dealing with electric circuits in grade 12. Maybe it would be proper for me to introduce myself. I am Mutsinyan Litina, subject advisor for physical sciences in the Karib district. So as I've indicated today, the broadcast is based on electric circuits, and this will also include internal resistance. We'll see how we build it in. I have with me or what I have brought today that I think we are going to make use of is a program that I have found, if I may say it's a program or an applet that I have found on the internet. We will try to give you the website where you can access this. I hope it is going to help us, especially the teachers, because you may know, colleagues, that sometimes you prepare a circuit using the real bulbs and batteries, and only to find that when you get to the classroom, one of the bulbs just decides to blow and then everything fails, or sometimes there is a loose connection somewhere and you end up having to troubleshoot the circuit, and then that may somehow interfere with your lesson. So I've thought of making use of this DC circuit breaker as a tool that we can use, and we will see how it can we can use it also to assist our learners in answering some of the questions in the exam as well. And even for learners, they can access this and they can practice on the circuit itself. So my main focus will be to try and see how we can apply this. So one of the websites where you could possibly get this is the physics classroom. If you just Google physics classroom, then you will find this circuit builder. It is incorporated there, but there is also a website where you can access this. So it will depend on you. We will provide you with the website where you can get that. Colleagues, I've also not interacted with this applet for long, but I think I have gathered enough information for us to be able to use it. So I would encourage you, even if it's you as a learner, just play around with this circuit builder, build your own circuits, try some questions on the exam question papers, and then you'll see it will help you. There are a few things that maybe I will need to clarify as I probably introduce this circuit builder to you. One of these, if perhaps I can quickly build a circuit, is that it has a few drawbacks, but I don't think the drawbacks are as important as as you can see, with us, we use conventional current, where we would say positive charges move from the positive terminal of the battery to the negative. So in this case, in this circuit, they show positive charges moving from the negative terminal to the positive terminal of the battery. So I think that is one thing that you need to be aware of. The other thing is this battery of ours here is just represented as a single cell, like a 1.5 volt cell. But of course you can be able to adjust the you can be able to adjust the voltage to 20 volts, 12 volts, 6 volts, 1.5 volts, depending on your needs for a particular circuit. So although it appears here as if it is just one cell, but we can, of course, refer to it as a battery. Other than that, I think, the other thing that I've noted is that if, for example, you put an ammeter in the circuit there, it only gives the values up to 1 decimal place. So in some cases where maybe you have in your calculations up to 2 decimal places, you might find that the app just gives you up to 1 decimal place, and it rounds off. So you may find that there has been no change in the values as you deal with, you alter the circuit, but only to find if you carry out the calculations and maybe go up to 2 decimal places, then what you find as a value in this app will be a rounded figure. So if you are aware of that, I think it can help you to clear some of the misconceptions that we can come across. I've tested it with a few circuits and it looked quite useful to me. Now I will try to introduce this circuit builder by just showing us how we can play around with it, and then from there we will get into our lesson. Perhaps the good point to start is for us to, if you want to remove any of the components, you just click on the X there, and then you don't need to click there several times. Once you have clicked there, you can remove the components that are there in the circuit. The other thing is you have your ammeter there, you have your bulb, you have your resistor, you have the connecting wires, the switch. Now when you want to draw a circuit, you click on the draw to place wires icon there. Then you will select the icon you want to place on the circuit. Here I have selected a bulb. Then you can put it anywhere where you want that bulb to be on the circuit. So you can see that once you have clicked on the bulb, then it is the active one, where whenever you click on the circuit, you are going to have your bulb placed there. Then you can connect, say maybe introduce a switch in your circuit. It's a closed switch. You can open the switch, you can close the switch by clicking anywhere on the switch there, I think. Then you can finally put connecting wires. So once you have clicked on the connecting wire, then you have the opportunity to place your wires wherever you want to. If you want to open the circuit, you can open the circuit by opening the switch. So that is how it goes. If you click on this icon, you'll see you have your voltmeter and ammeter. I did not have enough chance to play around with this, but you can also try it, colleagues. What I've seen is that it takes a little bit longer, and maybe as one of the drawbacks also is that you have to connect the positive, just want, let's say, across the bulb there, you have to connect the positive, if I'm not mistaken. You have to connect the positive to the negative in order to get a positive value there. So you can also move this so that it can be seen. Now what I want you to note is, instead of using a voltmeter on the circuit itself, or on this circuit itself, you can notice that this reads 4.5 volts. You can make use of a facility that they have incorporated in here, and that is, at each point of the circuit, they indicate the voltage at that particular point, or the potential at that particular point. So I think this can also help us to explain the concept of potential difference, in the sense that, let's take this bulb for example. This says there's a potential of 9 volts because the battery's voltage is 9 volts. There's a potential of 9 volts at one end of that bulb. The bulb makes use of some of the energy, and when the charges go past the bulb, you have a potential of 4.5 volts. So the potential difference now will be the difference in the potential between the 2 points across the bulb. So that will be 9 volts minus 4.5 volts, which gives you 4.5 volts. You'll also see that the same potential across this conductor is found on both ends of the conductor. So you have 4.5, let me say 4.5 volts at one end and 4.5 volts at the other end. So the difference in potential there is 0, and that tells you why there won't be a potential difference in a conductor, because there's no energy loss in that conductor. You get to the next bulb, you have 4.5 volts on one end and 0 volts on the other end. So the potential difference becomes 4.5 minus 0, which is 4.5 volts. So I think that there may not be a need for you to use a voltmeter, as long as you remember that to find the voltage across a component, you just take the difference in potential between the 2 points, or between the 2 ends of the conductor. As I've indicated, you can change the parameters, the resistance of the bulbs, the resistance of the resistors, and you can also change the voltage of the battery, and I will just show you how we can do that quickly. Now when you click on this icon, that's where you adjust. I think this shows that's where you adjust. So it gives you, you have that lens, it indicates where you are paying your attention. So in this case, our attention is on the bulb, sorry, on the battery. You can change the voltage. I've seen that if you click on this arrow here, it gives you the 10. So if you want 10 volts, then you will do that. If you want 20 volts, you click on this side to get 20. 25 volts, you will go up to there. If you want 9 volts as we did, then this becomes 0, and then you click up to 9. That is what we have. If you want to go to the bulb, then you can change the resistance of the bulb. In this particular case now, the resistance of this bulb is 10 ohms. So you can change that using the same approaches we have done for the battery. The same thing applies if, say for example, here we removed this. So you go there, you click on the cancel button, and then you can have your resistor located there. So if you want to change the resistance of this resistor, you will just click there and then go to the resistor, and then you can change the resistance of the resistor. But for now, I will leave it at 10 ohms because of the activities that I would like us to do. So basically, this is what you have, colleagues. And so you don't really need, if, for example, you close the circuit, then all you need to note is the difference in potential between this and that. Now, if you want to put an ammeter at any other point in the circuit, maybe you will need to open the circuit there and put an ammeter. So you can have, in essence, an ammeter and a voltmeter across a component here, and an ammeter connected in series with the components. So you can read the potential difference, which in this case will be 9 minus 6. That will give you 3 volts, and then you also have the current in there. So you already in here you have an inbuilt voltmeter, and an ammeter can also be added to the circuit so that you can record both the voltage and the current. So like I said, there's really no need for you to use these tools, although they are there. But if you like, you can, in order for one to show that a voltmeter has to be connected in parallel to a component, while an ammeter has to be connected in series. Colleagues, I think that explains a bit about that. You can explore it further, and perhaps you'll be able to get more out of this, as we will see as we go on. So as I've said in my introduction, that sometimes, colleagues, we find it difficult to build circuits for our learners. I think we can also be able, now that we can access this applet, we can be able then to set up circuits and let our learners play with the circuit and the components. And here I think there is no, you don't have to worry about saying I will ban a certain component. Everything can work if all goes well. So I've designed activities. In the first activity, colleagues, we are just going to look at a simple series circuit. We will build that simple series circuit, and I have an activity like this one, where you can use that for a series circuit, and then we will build the circuit. And here I already have a screenshot of that, so that when we refer to R1, R2, etc., you can be able to do that. Colleagues, once you have a screenshot of that, you can paste it on a Word document. This is a Word document. Then you can add text boxes to put in these labels. That is what I have done. Now, in this circuit, what we expect the learner to do is to connect this, the circuit with 2 resistors connected in series. So these are the resistors that are connected in series, but we'll build that circuit. As I've indicated, this is just a screenshot. Now, the learner will be expected then, after setting up the circuit, to record the following: the total voltage, the voltage across resistor 1, voltage across resistor 2, the current through resistor 1, the current through resistor 2, and the total current. And then there are questions that learners can answer there. So we are going to build this circuit, and I will expect because I assume that learners are also watching this. I expect them to do those recordings, and then we can come up with conclusions based on what we have on that particular activity. This activity, colleagues, as I've indicated, or as I'm indicating now, is just what I thought of that we can use in order to build the relationship between the variables. So it is not cast in stone. Any one of us can change it. It's in a Word document. You can change it. I think I will try to arrange so that I send it to Mr. Velman's website, so that we can access it, the Lejweleputswa website, so that each one of us can access it, and perhaps you can see where you want to make changes. You are free to do that, so that you can be able to assist our learners. So it does not mean that everything here is fine and has been tested. I have not tested it, but I've just looked at a few things that we can use from here, so that we can be able to reach certain conclusions. So in this particular case, I'm going to quickly build the circuit, and then the learners, I hope you will quickly take note of that. In your workbook, you can just write V total, V1, V2, I1, I2, and I total, and then I will build the circuit, and then we will come back to this worksheet. So how are we going to build that worksheet? Sorry, how are we going to build that circuit? We will have a resistor. Let's put it here. And another one, perhaps I need to put it here. You know, sometimes the planing of the circuit board can be a challenge, because you need to also give room for other components. So I am thinking of having a switch somewhere there, and then connecting an ammeter here, and then another ammeter there. Then I think I can have connecting wires. So colleagues, notice that we have an ammeter. Already across this we have a voltmeter, because it is going to indicate for us the voltage, or the potential difference across the resistor. I'm using resistors here because normally our questions come with resistors, but you can still use bulbs, I hope. So in this case, then you connect that circuit like that. We will take this resistor to be R1 and that resistor to be R2 as indicated in the and then I will, well, you see the switch is closed, but there's no current flowing. It means the circuit is open somewhere. Now I notice that we still have to put another connecting wire there. If you open that switch, there it goes. Now what we want to say is we have our battery with a voltage, or EMF if you want, of 9 volts. And then when we close that circuit, then you can record the voltage across this resistor, which is the potential difference across that resistor. Remember, we call it R1. You record the voltage across this resistor, R2, and your total voltage, that is the EMF or the voltage generated by the battery, will be this much. And then you look at the current. I1 represents the current through the resistor 1. I2 represents the current through resistor 2. I hope you'll be able to see these values. And with that, then what I did was, from this circuit, then I just took a screenshot of this and then I put it on the Word document. Perhaps that is where we should go. If you have not recorded those, I think I already have that screenshot. You can look at the values if you can see them. So you see, in this case, the resistor R1 is covered by, partially covered by this positive charges moving through the circuit. So that is why it's not easy to see this, but R2 is there as well. So you can take the same values that we have here are the values that we have on that circuit. Let me give you a few minutes then to record your findings. Just check for me, what do you find to be the relationship between I1, I2 and I total? I just assume here you will have to figure out what I total will be. The second question says, what is the relationship between V1? Remember, V1 we said is the voltage across R1. V2, the voltage across, or the potential difference across R2. And V tot will be the voltage across the battery. So you can see here, maybe what we could also have added is the current through the battery here. I think that would be our I tot. Perhaps we can add that. So it means you will have to change this for a better result. So perhaps let me go back and change that so that we, let's say now we put an ammeter again just after the battery there, so that you can see what the I tot is. So you can complete that for I total. Have you found the relationships? Yes, we will discuss them. Then I would request that you use Ohm's law to calculate R1 and R2, or even the total resistance of the circuit. I think this is also going to help us. R1, R2, and the total circuit resistance. R1, R2, and the total circuit resistance. I think using the information you have here on the circuit, you can be able to do that. Or the values that you have actually noted down. Then the last question says, write down your conclusions based on this activity. What can you conclude? You can perhaps start like for resistors connected in series. This is what you have noted about the relationship there. For resistors connected in series, that is what you have noted about the voltmeter readings there. That would be your conclusion. Okay, let's see how we can look at those. I hope you have those questions with you. What I've recorded here is that the total voltage or the potential difference or the EMF, if I may be correct, of the battery is 9 volts. The voltage across or the potential difference across R1 is 9 volts minus 4.5 volts, which gives us 4.5 volts. The potential difference across R2 is 4.5 volts minus 0, which gives us 4.5 volts. Now remember, these resistors are connected in series. What can we conclude from these figures that we have found? We notice that the total voltage across the battery is equal to V1, which is 4.5, plus V2, which is 4.5 volts. So if we have our resistors connected in series or in a series circuit, V total will be V1 plus V2. If you have other resistors, then you have plus V3 and so on and so forth. But for the current, if we noted that the total current is 0.4 volts. The current through resistor 1 is 0.4 amperes, and then the current through R2 is 0.4 amperes. So it appears, as we look at this, that the current through the circuit is the same at each and every point of the circuit. So the total current is equal to the current through the resistor R1 is equal to the current through resistor R2 is equal to the current that passes through R3 if these are connected in series. So this is, I think, an important point that we need to note from these readings. And it is one of the conclusions. So in your conclusion, you can indicate that in a series or for a series circuit, I total is equal to I1 is equal to I2. V total is equal to V1 plus V2 or plus V3, depending on the number of resistors that you have in there. Now, I've quickly used the data that we have there to calculate the resistance of this. You will note that if I were to go back to this circuit, you will note that let me just open that and check the resistance of this resistor. I don't know how you did your calculation, but I think you'd have taken, because we have the current through the resistor, and you have the potential difference across the resistor, then using Ohm's law, R is equal to V, the voltage across, or the potential difference across the resistor, divided by the current through the resistor. That gives you the resistance. Now what I wanted us to check is the correctness of that value, and then we will look at that. If we look at the resistance of this resistor, it is actually 10 ohms. So in our calculation, using the voltage or the potential difference of 4,5 volts and the current of 0,4 amperes, we find the resistance to be 11,25. You can check that. I think the one way of checking that is if we are given that the resistance according to the settings in the program is 10 ohms. You can actually check that the current in the circuit ought to be 0,45 amperes, so that you get a resistance of 10 ohms. But for the very same reason that I indicated, that this circuit rounds off this figure to 0,4 instead of 0,45, that has given us a resistance of 11,25. But I don't think that has any effect on what we want to establish here. We are using Ohm's law. Ohm's law says the resistance across any conductor will be the potential difference across the resistance of a conductor or a component like a resistor will be given by the voltage or potential difference across that resistance divided by the current. So that is what we get. So we need really not worry about this, but also take into account that factor that I've indicated, that the program or the applet rounds figures off. So for R2, we also get the same resistance. So for the total resistance, we just add the resistances R1 and R2 so that we get a total of 22,5 ohms. If we were to go with the 10 ohm resistance as the value of that, then we would just add 10 plus 10 and get that as our R total, which is 20 ohms. So that is what we have there. That is for the first activity. Let us note then, colleagues and learners, that the total current for a circuit is given by the sum of the total current is the same throughout the circuit. So I total will be I1, will be I2, will be I3, depending on the number of resistors in the circuit. The total voltage or the EMF of the cell, if you like, or of the battery, will be V tot, will be equal to the sum of the voltages across the components. So we normally say that in a series connection, these resistors become potential dividers, because now if you have a voltage of 9 volts, that is divided between the two resistors R1 and R2. But it should be noted here that in this case, our resistors each is 10 ohm. So the voltage across each one of the resistors will be the same. However, if we had resistors of different values, then the voltages here would not be the same. However, their sum will still add up to the total voltage. This is what you can try yourselves, colleagues and learners, to check what happens if I change the value of resistor 1 and the value of resistor 2. Then will I still get the same relationship where we say the total voltage across the battery will be equal to the voltage across R1 and voltage across R2. So this is one thing that you can do on your own, just to experiment and get more clarity on that. The next activity that I thought we should look at is we are going to look at a parallel circuit now, and we will build that circuit as we have done in this case, and then you will also record the values V total V1, V2, I total I1, I2, and you will answer those questions. Let's build the circuit. So notice that for this circuit that we are going to build, now we are going to have resistors connected in parallel. So I may as well take this resistor, put it there, and then let's see, this requires a little bit of, okay, let me connect a wire here. I will connect a wire there. I have a feeling that we can have an ammeter there. So we have an ammeter here, we have an ammeter there. I want to add another switch here, just for interest's sake. But we'll keep this switch closed for now. And then we will have our ammeter from the battery there. We'll have our ammeter from R. Now we can call this R1 and that R2. I don't know how I put them on the other circuit, but let's call that R1 and R2. And then, of course, because this switch is still open, no current is flowing, but if we allow the circuit, we close the circuit, then you'll see current is flowing. Perhaps we can, or we are not going to check the resistance of the resistors. We will just carry out the same procedure as we did with the other activity. So I think you can see how I came up with this screenshot. It has our two resistors connected in parallel, and then we have our ammeters there, and we have the switches. I've included switch 1 there, S1 there, for a particular purpose. Now let's look at the readings. Where are we now? I think we should be here. Let's take the readings from here. Remember we said V1, V2, V total, and then you have I1, I2, I total, and in this case now our resistors are connected in parallel. Yes, I was quickly also trying to use the information here to do the calculations. I think you have recorded these values for the parallel connection. And what is the same as the first activity? What is the relationship between the I1, I2, the current through resistor 1, the current through resistor 2, and the current through the whole circuit or through the battery? What is the relationship between the voltage across the R1, the voltage across R2, and the total voltage of the battery? Then use Ohm's law to calculate R1, R2, and the total circuit resistance. Then write your conclusions based on this activity. I think you have already done that. So we will move to what I have here, what I have recorded. You can see that instead of recording the current here, the voltage here, I recorded the current. So these are some of the things that the mistakes that we make. But let's quickly look at what you have. You probably have noticed that the voltage across the battery is 9 volts, or the EMF of the battery is 9 volts. And the voltage across R1, it was 9 volts on one end and 0 on the other end. The potential was 9 volts at one end and 0 at the other end, which gives us a difference of 9 volts. The potential difference across V2 was also 9 volts. And what relationship do you make of this? Now you see that so this is for parallel circuits. So for a parallel circuit, the total voltage, or the voltage across battery, will be equal to the voltage across the parallel components. If we have two resistors, only two resistors in there. And then, or wherever you have parallel components, then the voltage across one component will be the same as the voltage across the other component. But with the current, what you should have noticed is that the current through the battery was 1.8 amperes. The current through R1 was 0.9 amperes. And the current through R2 was 0.9 amperes. Now, what is the relationship here? You will notice that I total is the sum of these two. 0.9 plus 0.9 gives you 1.8. So these are the conclusions that I think we need to put there. For a parallel circuit, V tot is equal to V1 is equal to V2. And I tot is equal to I1 plus I2. In other words, what we are saying is that in a parallel circuit, that total current that goes through the battery, at that point where you have a junction where the current can go both ways or in different directions, then the current divides the one-to-one resistor, some current to one resistor, some current to the other resistor. So these resistors are said to be current dividers. They divide the total current in the circuit between themselves. If there are two, if there are three or more, then they will divide the current amongst themselves. So the total current is given by the sum of the current through R1 and the current through R2. If you have a third resistor and the current through R3, so when you add these two currents, they must give you the total current. I think now you can see how this really works. It can help us understand some of these things. So going back to the questions, I think the other question said you calculate the resistance of R1. So in this case, we will also confirm if that is correct. R1, I think the figures here are very good. You get V1 is 9 volts. The current through R1, the voltage across R1 is 9 volts. The current through R1 is 0.9 amperes. Therefore, by Ohm's law, the resistance of R1 is 10 ohms. We do the same for R2. The voltage or potential difference across R2 is 9 volts. The current through R2 is 0.9 amperes. Then you get a resistance of 10 ohms. Perhaps we can, if you like really, just to say, let's see whether this resistance of this resistor is actually 10 ohms, and this is what we get. So these resistors, if you like, you can say they are identical. Hence why the currents through them are the same. But if you had resistors of different values, then you can try that as well. Check the relationship between the current that will pass through one resistor and the current that will pass through the other resistor, and make your conclusion. But what will remain the same here is that the sum of these currents will add up to the total current through the circuit. Now, by now you'll probably know that to get the total resistance of parallel resistors, sometimes we call that, instead of referring to it as total resistance, we refer to it as equivalent resistance. In other words, what do we mean by equivalent resistance? We are saying that if you have two resistors connected in parallel, you can replace these two resistors with one resistor, with a single resistor, which will have, you can say R equivalent or R total. That resistance or that resistor will have the same resistance as these two parallel resistors. What this means is, for example, for somebody who's working with resistors, say repairing circuits or building circuits, this person finds that I have two resistors that are connected in parallel. Say one is 10 ohm, or maybe it's in both of them are 10 ohms. Then this person realizes that in my kit I do not have two 10 ohm resistors, but I can use one resistor which will give the same resistance as the other two resistors. Then that person can simply remove these two resistors that are connected in parallel and replace those with one resistor which has the same resistance as the two resistors. So that is why we call that equivalent resistance, equivalent to the resistance of the parallel resistors. So how do we calculate that, we use that relationship to say 1 over R total or 1 over R equivalent. Sometimes we say R parallel. 1 over R parallel is equal to 1 over R1 plus 1 over R2. 1 over R total then will be, we substitute 1 will be 10 over 2, which is equal to 5 ohms. So that means if we were to replace these two resistors of 10 ohms each by one resistor that has the same resistance as two resistors, we would replace them with a 5 ohm resistor, and that would be our equivalent resistance. So the key things to remember here are that for a parallel circuit, the total voltage there will be equal to the voltage across V1 and the voltage across V2. Or for any parallel components, then you will have that relationship. The total current in the circuit will be the sum of the current, the individual currents through the resistors. These are the basic elements of electricity and or electric circuits, and when we get to internal resistance, you'll see we will be applying this as well. Hence why I thought maybe let's start with this so that we can also recap on the knowledge that you already have. And I think in a way we are already doing the experiment that the teachers are supposed to be doing, and maybe with slight modifications there you can find this helpful, colleagues. Let me just check. Okay, on this very same circuit, I have an extension. Maybe after this we will take a short break. I have an extension here. Now, the extension is on that circuit that we started with. Now we open switch S1. And then you can make recordings of what you find. And what I would like you to look at here is, what is the difference between the total current in this circuit and the previous one where both switches were closed or are closed? What would be the difference between the total current? So we will look at the total current through the circuit, compare that with the total current when these two switches are closed. I think that is an important thing to note. Then we will also check what is the voltage across R1. In other words, what would be the value of V1 across this resistor? How does the voltage V1 in this circuit compare with that in the previous circuit where both switches were closed? Now we will look at V1, the voltage across R1, compare it with the voltage there when the two switches were closed, or when this is closed and that is closed. And then you can use Ohm's law. I think we will not do this for this activity. You will do it yourselves, but what is important is for us to see. And then the last question says, how does the total resistance of the circuit compare with that of the previous circuit? In other words, how will the total resistance now of this circuit be compared to the total resistance when switch S1 was connected or was closed? Let's look at these relationships and see if we can be able to make any observations. So these are the current readings and the voltage readings before switch S is opened, when both switches are closed. Just take note of that. Maybe we can take them individually. Let's look at the total current when we open this switch. What happens to that total current there? I think we will also have to check whether this has not been rounded off. We will have to check that if this has not been rounded off. And then let's close this and also check the voltage across this. Before we said it's 9 volts. If we open that switch, what is the voltage there? It still says 9 volts. We will have to check if there's no rounding off there. But what is the voltage across this resistor R2? The voltage across this R2, of course, will be 0 because there is no current flowing through this circuit. Immediately we open this switch, this branch switches off. We will have to look at this if there is no rounding off. We will work it out and then we will argue out also so that we can see if maybe there's nothing wrong with the circuit. And then what else were we supposed to check? The total resistance. Now let's look at the total resistance. Before this we said the total resistance was 5 ohms because we basically half the resistance of this. In other words, when there are two resistors connected in parallel, the current here is actually supposed to be more because the resistance of the circuit is smaller. When we open this, now the only resistance that is in that circuit is a 10 ohm resistor, which means that resistance is bigger than the combined resistance of the two resistors. So we actually ought to have a smaller current flowing through here. So that is why I'm saying let's check if maybe rounding off has not taken place here, because we ought to have, let's check that. Well, that was 1.8. Yes, that was 1.8. If we open that, the current becomes smaller because the resistance has increased. So I think that is applicable. So let's see how this relationship is important. Notice that when switch S1 is closed, the equivalent resistance of the two resistors is lower, and as a result of that, the circuit resistance is lower, hence more current flows through the circuit. But if you open that branch, you are killing off this branch. There is no current flowing through this resistor. The resistance that we have here now is higher than it was before. So the total circuit resistance is higher, and the total current by using Ohm's law will be lower. I think that is the relationship that I wanted us to have a look at there. So you can work on that activity, but look at that relationship. It is a very important relationship that you will also come across when you deal with questions in your exam. Perhaps we can take a 5-minute break at this point, and then we'll just look at the last activity, and after that then we will look at internal resistance, and then we'll incorporate this information that we have tried to compile in this particular lesson to now transfer it to internal resistance, which is, I think our question papers as well are mainly consisting of questions on internal resistance. So we will just take it from where we have stopped, and then we'll link it with internal resistance and see if we can be able to make use of this information. Welcome back, colleagues and learners. I already have before me here the circuit that I would like us to do in the third, and what I will probably say is our last activity for this lesson. Although you will need to record all this information, I think what I will try to do is to just effect those changes on the circuit and see what happens. Then learners can complete the information and see if they can make sense of that information. So you need to record. Notice that here we have a series parallel circuit. You have R1 connected there, R2 and R3. So R1 is connected in series with R2 and R3, which are connected in parallel to each other. One thing that I've noted that learners sometimes have a challenge with is when you say components are connected in parallel, for them they have to be placed side by side, which may not necessarily be the case. So what probably we need to, and I know colleagues are showing our learners that whenever we have a branch where the current takes two or more paths, that's where that signifies a parallel connection. So in this case, that is the type of scenario also that we have in our question papers as well, and it might help for our learners as well to understand the, can I say the dynamics or the principles behind that. What happens when we do this? What happens when we do this? Then they can be able also to argue in a logical manner in trying to answer questions based on what they have actually experienced and seen on the circuit board itself. So the questions here are, you have both switches closed, so you'll have switch 1 as switch S2 closed, and then you will record the total voltage of the battery V1, that is the voltage across the resistor R1. V2 will be the voltage across resistor R2. V3 will be the voltage across the resistor R3. And then the I total will be the total current through there. You'll see that in this circuit I did not have the ammeter right here next to the battery, but you can do that on the circuit board, colleagues. So we want to find the relationship. What is it that we find interesting, striking about this? Then if you like, you can also calculate R1, R2, R3 and the total circuit resistance. This is important to calculate the total circuit resistance. You have information here, but now for the total circuit resistance, notice that we have this parallel branch here connected in series with that. So you need to find the equivalent resistance of this, then add that to R1, which is in series with these two resistors. So that would be the total circuit resistance. So I think for practice also, learners, you also have to do that, so that with more and more practice you can be able to get the concepts clear. So this is the circuit that I've set up. When both switches are closed, we can record the values. The current through the battery there is 0.6 amperes. The current through R1 there is 0.6 amperes, and one will ask, why are these two the same? And then we go on, the current through R2 is 0.3 amperes. The current through R3 is 0.3 amperes. Now already you can see that relationship that we talked about, that the sum of the currents in the individual resistors connected in parallel, 0.3, 0.3, adds up to the current in the second. I total is equal to I1 plus I2. 0.3 plus 0.3 gives us 0.6 amperes. This 0.6 amperes is the current flowing through R1. R1 is in series with the battery, so the current through the battery is 0.6. So the current, the total current in the circuit is 0.6 amperes. Now I am no longer following the activity exercise that you can do as well, colleagues. I'm just trying to analyze what I see here and what perhaps you can also check. Now let us see. R1 is connected, that is why we say this is a series parallel connection. R1 is connected in series with the two resistors that are connected in parallel. If we use that relationship, that R1 and these two resistors in series, in parallel, are connected in series, then R1 and R equivalent of these two resistors will be in series, and therefore they will what can I say? They will share the potential difference or the EMF of the battery. They will share the total voltage of the battery. If we take the voltage across R1, it will be 9 volts minus 3, which gives us 6 volts. The voltage across R2 and the voltage across R3, because they are connected in parallel, must be the same. It is 3 minus 0 for R2, which is 3 volts. It is 3 minus 0, which is 3 volts. The voltage across R2 and the voltage across R3 are the same. So the total voltage of the battery, which is 9 volts, will be the sum of the voltage across R1, which is 6 volts, plus the voltage across this parallel component, which is 3 volts. V total is equal to V1 plus V2. Now, you'd see if perhaps I close this, and notice that this one now closes the whole circuit, so it breaks the circuit, and it breaks the circuit, or it opens the circuit, not close, and therefore no current flows at all. So what I just wanted to check is, or verify, is the resistance of this resistor. R1 is 10 ohms, R2 is 10 ohms, R3 is 10 ohms. So it makes sense then to say if this the resistors are identical, when we close that switch, the current through R2 must be the same as the current through R3. Now, what you can do as a variation, colleagues, is you can change the values of these resistors and look at the relationship between the currents through each one of the resistors and the total current. Notice in this case that the currents add up to that, as I've indicated. So this is the scenario. Now let's take it further and open switch S1. With S1 closed, the current, the total current here is 0.6. Let's look at that total current when we open that switch. It drops to 0.4 amperes. And why is that? We have deactivated this branch of the parallel circuit. Now we are left with two resistors that are connected in series. 10 ohm, 10 ohm. That gives us 20 ohms. So the total resistance is now higher than the total resistance when these were connected in parallel, or when this switch was on, or yes, when this switch was closed, because these two have an equivalent resistance of 5 ohms. The total resistance of the circuit would be 5 ohms plus 10 ohms, which is 15 ohms, with switch S1 closed. So that makes the current through the circuit to be higher because the total resistance is lower. If we open that switch, as I've indicated, now we have two resistors in series. We have a total resistance of 20 ohms. The current decreases, the total current in the circuit decreases. Colleagues, I think this would also be interesting if we did it with bulbs. You know, get the bulbs and also look at the brightness and things like that. So I think this really has a wide application we can explore and find ways of trying to understand how our circuits work. Let's look at the voltage. When switch S1 is closed, I think we talked about that already. The voltage of the battery is 9 volts. The voltage across this one, R1, is 6 volts, and the voltage across the parallel one is 3 volts. So the two voltages of the across the resistors adds up to the total voltage or EMF of the battery. If we open switch S1, the voltage of the battery still remains 9 volts, the EMF still remains 9 volts. What has happened to the voltage here? 9 minus 4.5 gives us 4.5 volts. It looks like the voltage has gone down. Yes, from 6 volts to 4.5 volts. And here also we have a potential difference of 4.5 volts. Now notice here that the potential difference across each one of the resistors, it makes sense because these two resistors, each is 10 ohms, that is 10 ohms. So the potential difference across this one will be the same as the potential difference across that one. The sum of these two are still going to give us the EMF or the voltage of that. But what we have noted is that the current here in this circuit decreases because now the circuit resistance or the total circuit resistance has increased. Colleagues, find ways also of explaining further, this further. I may not maybe have exhausted all the things that you might, our learners might encounter in the examination, but I think this gives us an idea of how we can use this. In the next program, what we are going to do now is to look at past exam question paper. I will talk about internal resistance, sort of introduce it and maybe show our learners how they can treat a circuit with internal resistance, and then from there we can look at a few questions from the past exam question papers, and at the same time make use of this particular program to set up the circuits as they are in the exam question papers, so that learners can be able to use these circuits that they have built to try and organize their thinking and reasoning as to why a certain circuit behaves in a particular way. I hope this sums up our lesson today. It was mainly to introduce this circuit builder, and at the same time to recap on those basic concepts of series connection, parallel connection, and series parallel connection, and look at the relationships between the physical quantities or parameters in each of the individual circuits. I just hope that this circuit will help most, if not all, of our learners to do well, and also it will also help our teachers to be able to explain and demonstrate some of these concepts, because electricity is really a practical subject. One needs to see something happening, otherwise it can be very, 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 very abstract. Colleagues, let me thank you for your attention. Let me thank you for your participation, and I hope we are going to do better in electricity. With that, I would like to bring this lesson or this broadcast to an end for today. We are meeting tomorrow.